Hello everybody, today we are going to talk about Fresnel Biprism experiment. So in the last class I have shown you the method by which we can get the coherent source. So the thing is that is not the only method by which we can get the coherent source. So there are few more methods by which we can get the coherent sources. So the first method was proposed by Young with his idea of double slit. So using a single source and putting the double slit near to it, we can create a coherent source, and that coherent source will give you the interference pattern, and we'll study that pattern. So what Fresnel did is, Fresnel came up with his new idea of production of coherent source. Okay, so idea is something like this. He used a biprism to get the coherent sources, and I'll tell you how that biprism will give you a coherent source. You see now, what he did is, he took a biprism. This is the biprism. Bi means two. Actually, he used biprisms. Here's the one, there's the other one. What he did is, he joined two biprism with their bases, and he took the angle of this acute angle as half degree, or you can call it as 30 minutes. And similarly, same here also he took as half degree or 30 minutes. So the overall is going to be 180. So the remaining this angle will be 170 degree. So this is the biprism. So now you see the importance of the biprism. It is playing so much important role in producing the coherent source. Okay, so what Fresnel did is, exactly in front of, in a same line, what he did is, he put a source here. I'm naming it as S. So this source will give light in all directions. So the light will fall on the prism, something like this. Okay, so we know the angle of incidence and angle of refraction from the geometry, from the ray optics. We all studied those things, and because of this angles, you see, this prism is not any kind of mysterious material. We are just taking glass, and the important thing is that at what angle the glass is cut. Okay, the cutting is important, the angle of the glass is important, and that is how we are getting coherent sources. That is important here. So it is just a normal glass. So what makes it so special is this angle, the cutting of the biprism. Okay, so normally if you take a plain glass, the light will go straight like this, no deviation. But because of this angle, it will go something like this, and from here the ray will bend towards the base of the biprism. So here's the base, the light is little bit bending towards the base. Why not the light is going straight like this? Because of the angle. You see, because of the angle. So that is the secret of getting coherent source. You see, now you'll get to know about it. Just wait. So here's the final screen. Similarly, this light ray will also get bent like this, and this is the straight one. Okay. Now this light ray will also get bent. Actually it should take something like this path, but because of the cutting, because of the angle of the prism, it will bend towards the towards the base of the biprism. Similarly, these lights, this light will also bend. So because this upper light ray got bent towards the bottom, so the bottom ray will bend towards the top. Something like this. And this ray from here will be moving something there. So this is the region where you will get the interference pattern. How? The thing is, we have studied, if we want to get the interference pattern, we should have the coherent sources. But where are they? Where is the coherent source? The coherent source, actually this is a single source. We know that if you want to have the coherent source, if you want to have the interference pattern, we should have the coherent sources. But you have just a single source and you are telling that you will get the interference pattern on the screen there. How is that possible? It is possible because of this prism. What prism actually did is, you see, I'll explain you something like this. This is the whole wavefront which was coming from the source. It is something like that. So this is the whole wavefront which was coming from the source, and after passing through the biprism, what the prism did is, the prism changed the angles. You see these light rays are going like this. So after coming out, the half wavefront, the 50% of the wavefront is going like this, and the other 50% of the wavefronts are going like this. Okay, so that's how you have created two sources, two individual sources which are having same wavelength, same frequency, and they are in phase. Why? Because they came out from the same source. So that's how they will meet here in this region. So you will get the interference pattern in this region only, not here. Why? Because here you are just having a single source light here, and here also you are having a single source light. But this is the region where the two sources lights are getting merged with each other. This is the point where they are getting merged with each other. That's why you will see the interference pattern here with the help of an eyepiece. You will be having an eyepiece here. So with that you will see the interference pattern. Okay, so if I am getting the interference pattern over there, what it demands is, like, if you are getting the interference pattern, there must be two sources. So actually those two sources are these. So the light ray from here, so this is the source S1, and similarly this is source S2. So with the help of the biprism, what we did, we have created a coherent source. Okay, so it seems as if you're getting light from here, light from this direction, it seems as if there is some source in here and which is producing this light, and after seeing this light, it seems as if like there is some source here which is causing this light. Okay, so actually these are just virtual sources which are producing interference pattern. They are not real, they are just virtual sources created by the biprism. And we know the distance between the S1 and S2, we call it as D. Okay, now, so our aim is to find out the wavelength of this source S. So I've taken a source whose wavelength I don't know, and the thing is, I want to find out the wavelength of that source. So what I do is, I will put that source in here in this experiment, and I'll find out the wavelength with the help of a simple formula. We have seen from the Young's double slit experiment, if you have a source, and that source light is passing through the slits, it will produce an interference pattern on the final screen. And here's we'll get the fringes, dark and bright, and the fringe width we got it as beta. So in the Young's double slit experiment, we got the expression for beta fringe width. It was beta is equals to lambda L by D, where L is the distance between slits and the final screen, D was the distance between two sources, and lambda was the wavelength. So from here lambda is equals to beta d by L. So by using this formula, I can find out the unknown thing, which is lambda, the wavelength. Okay, so I can find out wavelength by using this formula. So I'll be using this formula in this experimental setup. Okay, so what I need for that, I need to know the beta, I should know D, and I should know what is the L. So we are performing this experiment. This experimental setup is actually on a table. This is a bench. There's kind of something kind of a bridge kind of thing on which we are putting the stand of Biprism, the stand of source, and the stand of eyepiece. So if you want to get the interference pattern in here, there is a condition for that. That is, the eyepiece and the biprism baseline and the sources should lie exactly in a single line. There should be exactly aligned in a line. Then only you can see the interference pattern. If suppose the source is something like this and the biprism base it is something like this, you won't get the interference pattern. If you want to get the interference pattern, there should be some symmetry, there should be some alignment between the source and the biprism, and then only you can see the interference pattern. That's a condition to have it. Okay, so now we will find out the fringe width beta. So here's the fringes. What you do is, for finding the fringe width, there will be a movable microscope here. This is the movable microscope, and there will be a vernier scale on it. So first what you do is, put your eyepiece at some particular fringe, set your crosswire exactly on any one of the fringe, either bright or dark. Okay, so I'm putting it on dark fringe, my crosswire of the eyepiece. I'll note down that reading. It will be some reading, suppose 5 millimeter. I got the reading. So what I do is, I'll move 10 or 20 or 30 or 50 fringes depending on your accuracy. If you want to get more accuracy, take more fringes. If you want just a small accuracy, take just few fringes cross. So what I am doing is, I am crossing the 10 fringes. So what I do is, I'll move slowly by rotating the screw. I can move the fringe. So I have moved across first fringe, second fringe, third fringe, fourth fringe. Likewise, I'll be moving across the 9th fringe, and now I am on the 10th fringe. What I do is, now I'll note down the reading now. So my eyepiece crossfire is now at 10th dark fringe. I'll note down the reading. So from here to here, it was 5 millimeter reading. So 5 millimeter divided by how many fringes you have crossed? I have crossed 10 fringes, so it will be 10. That will give me the beta value. This is how I can find out beta. Here's initially I have taken black, the dark fringe, so that's why at the end I am taking dark only. If you take bright, here also you have to take bright only. Okay, so now this is how you can find out the beta value. Now we will find out the L, which is the distance from sources to the final screen. But there is a problem with this calculation, is that the sources S1 and S2 are not real sources, they are virtual sources. So how you are going to take the reading from these virtual sources to the final screen? If they were real, you will just simply take the distance from here to there. But they are not real. So from which point you will take the initial point and take the reading to the final point and find out the value of L? That's the problem. But so the geometry of the figure will take care of it. You see from this figure, the S source is lying in a line between S1 and S2. So it is sure that the position of S1 and S2 is exactly similar to the position of S. So that's how, if you can measure the distance from S to the final screen, it means that you have measured the distance from S1, S2 to the final screen. So that's how. So with the help of this table, there will be a scale on it. We'll take the reading from S to the final screen. Why? Because S is lying in a line with S1 and S2. So that's why we can take the distance from S to the final screen. So it will give me the distance from S1, S to the final screen. Now, there's a challenging one. Now we have to find out the D value, the distance between the two sources. But there is a problem with this thing. This is a bit tricky one, because the problem is these two sources are not real. If they were real, we can simply take the scaling, we can simply put the microscope, movable microscope here, take the first reading on S1, note down the reading, move it on the S2, take down the reading, subtract the first value from the second value, you will get the distance D between the sources S1 and S2. But the problem here is they are not real. You won't get the image of those sources on the microscope. If something is not existing there, how will you find out the distance between them? That's the problem. So the Fresnel came up with this idea. His idea is to put a lens, a convex lens in here. That convex lens will merge these light sources light into the final screen, 2 points on the final screen. So what we do is, we'll put a lens here, convex lens. What this lens will do is, the light rays from S1 source are hitting on it. Okay, so the light rays from here, they are hitting on it. So with the help of this lens, the lens will focus the light from S1 source to a point. So with the help of this lens, we can focus the light from the source S1 and S2 on the final screen. So instead of getting the interference pattern, we'll be getting two sharp images of S1 and S2. But there are just two positions like that from the biprism to the final screen, where you can get the two sharp images of S1 and S2. So first we'll put the lens here. At some point we'll be getting a sharp images of S1 and S2 on the final screen instead of getting the interference pattern. So, and as you move the lens towards the screen, there will be another point where you can get the sharp images of S1 and S2. Okay, sharp images of S1 and S2. The lens should be such that his focal length should be 1/4 of the distance from the biprism to the final screen. Then only it will be useful. Then only you will get the sharp images of S1 and S2. So to explain that, I'll be using a different diagram over there here. So the thing is, we have two sources, S1 and S2. Here's the final screen. So here's the sources S1 and S2 and the final screen. So what we do is, we'll put a convex lens. Okay, so this is the first position. I am calling it as P1. At this particular position of the lens, I am getting the images of S1 and S2, sharp images of an S1 and S2. So why that is happening is because, suppose the light from S1, the specialty of this lens is that, because it's a convex lens, what it will do, it will bring all the light rays to a particular point. So all the light rays will focus at some particular point. Okay, so from this light or whatever the light will come, it will get focused on this particular point. So that's how we are getting, instead of getting the whole light, we are just getting a single bright spot due to S1 here. So this is the S1 image. Similarly, the light from S2 will get merged on the final screen. So the lens will focus the light here. So now here we'll be getting S2 image. Okay. So the distance from here to here, this is the object distance, and from here to there, this is the image distance. We have studied that in intermediate. Okay, so with the help of movable microscope, I'll be finding this distance and I'll call it as D1, and this is my D distance. Okay. Now similarly, now what I do is I will move, after calculating D1, what I do is I'll move my lens towards the screen. Now I'm searching for another position on which I can get the sharp images of S1 and S2. S1, S2, having distance D between them is the final screen. It's my lens. So the light rays from this source will get merged, will get focused at this particular point, and that's how we get the image of S1. Similarly, the light rays from this source will be getting merged at some point in the final screen, and that's how we get the image of S2 source. So that's how we get this thing. So this is D, and with the help of movable microscope we can find out this distance, and I'm calling it as D2. So now at this particular position I'm calling it as P2. The distance V will be this thing and U will be this thing. The distances will flip at this particular position. So this is your V now and this is your U now. So now for finding the D value, we will be using a concept of magnification. So from in this case at P1 position, the magnification will be D1 by D. What is magnification? Suppose if you have something which is having this particular length, and after passing through the lens, if this particular thing got this much, that particular thing got this much bigger, it got magnified. If you want to know how much, by how much amount the thing, the object got magnified, you have to take the length of the magnified image and you have to divide that length by its original length. You will be getting the magnification of the lens. So here's the magnification was D1 by D, and that will be equal to U divided by V. You see from the geometry, here's the D1 and this is the D. So D divided by D1 will be equal to U divided by V. So I can write this as U divided by V. Let this be equation 1. And similarly, I'll apply the magnification to the position P2. The magnification here is M is equals to the image distance D2 divided by D Now the distances got flipped. Now it will be V divided by U. Let this be equation 2. Now I'll be multiplying equation 1 with 2. What I'll get is d1 into d2 by d square, and this u v into vu will get cancel out, and be getting I'll be getting 1, and d will be equal to under root d1 d2. This is how we will find out d value. So now I have everything for finding the value of lambda. I have beta from the movable microscope, I have d by this method, I have L from the table. So this is how I can find out the value of wavelength of unknown source. Thank you very much.